Swayam Prabha. Digital India. Educated India.
Welcome everyone to another session of supplementary video, and in this video we will be doing some problem solving actually. Okay, so let's start. So let's say we are given a function f of x equals c x e minus x square over 2a square, where c is a constant that's given, a is positive, and x is greater than equal to 0. Okay, so those are the given conditions, and the question is calculate c. Okay, calculate c given that f of x is a probability density function. Probability density function. Okay, so this is quite straightforward. So we are given the probability distribution actually, and this distribution, we have seen a lot of other kind of distribution like the normal distribution, Poisson distribution, and let's say the Gaussian distribution, binomial distribution in the main lecture material. So this is another kind of a probability distribution that we encounter quite a lot in probability theory, and this distribution is, by the way, known as the Rayleigh distribution. Okay, so this is known as the Rayleigh distribution. Okay. So given this Rayleigh probability density function, the question is evaluate c. So this is quite trivial, as what we need to do is just impose a condition that the total probability over all possible states is equal to unity. Okay, so that means what we need to impose is the integral from 0 to infinity f of x dx equals unity. Okay, and since we know f of x in terms of c, we can substitute it. So this becomes 0 to infinity c x e minus x square over 2x square equals 1, and from dx equals 1, and from here if you evaluate, we can evaluate c by just, because c is a constant, you can take it out and then compute the integral. So this becomes 0 to infinity x e minus x square by 2a square dx equals to 1. Okay, so therefore from here you can calculate, given this, we can calculate this integral quite easily. So from here we can find out what c is. Okay, so if you compute the integral, you will see c comes out to be 1 over a square. Okay, so that's how we find out the constants that sits in front of, let's say, any kind of distribution, where you impose this important criteria of that the sum of all probabilities actually is unity. Okay, so next the question is, given the same probability distribution, compute the mean. So that means what they're asking is compute x bar, or expectation value of x. This is again quite straightforward, given without no c, that means we know the probability distribution. This is nothing but integral of 0 to infinity x f of x dx. Okay, so this becomes 1 over a square, the integral of 0 to infinity x square e to the power minus x square by 2a square dx. Okay, so from here we can directly evaluate the integral. We can compute the mean. Similarly, it can be asked that calculate the standard deviation. So the standard deviation, so to compute the standard deviation, we know that the square of the standard deviation, also known as the variance, is given as x square mean minus the mean whole square. Okay, So you see this quantity can be again easily evaluated, given that this we compute x from this, which we show, and x square mean is the second moment. As you can see, this is just integral from 0 to infinity x square f of x dx. Okay? That's what this term becomes. So if we substitute this term here, we get the standard deviation can be computed as the square root of x square minus x bar whole square. Okay, that's quite straightforward. Okay, so we will be solving more problems. As you can see, what we are doing is we are not showing all the steps, because the steps those are quite trivial, and based on, like, if we do each and every step, we will not be able to cover quite a bit of problems. So the intention of this problem solving sessions are to cover a variety of problems, and so what we will be doing is basically provide you the outline of the solution, okay, rather than the exactly step-by-step solution. And if there is any doubt, those doubts could be resolved either in the discussion sessions that we will have live, or in the NPTEL chat sessions. Okay. So next, let's see the next question. So let's say this is a little bit interesting. So let's say the question is, this is the question, next question, the probability that a monoatomic particle will travel a distance x, or more between collisions is given by C e minus x over lambda, okay, where C and lambda are constants. Okay, so that's the generic idea, and the question is that is, so you see this is given, so this is the probability of finding out, let's say, that a monoatomic particle will cover a distance greater than equal to x. Basically, it will travel a distance x or more. Okay? So it is probability of finding the particle at distance greater than equal to x. Okay, so that is given as this. So the question is, compute the probability density function. Probability density function. That means we have to find f of x. So that's the, okay. So let's see what we are given is, we are given that the probability of finding a particle will say, so it's asking that the probability that a monoatomic particle will travel a distance x or more. So that means x has to be greater than equal to, like, okay, let's put it in a different way. So let's see the probability where, let's say, x lies between two states a and b, let's say, given by the integral from a to b f of x dx. Okay, so that's the generic way that we understand. That's the probability of finding, let's say, x in the range a to b, okay, given the probability distribution f of x. Okay, but let's say now what we are asking is that x that the particle will travel a distance x or more, or distance x or more. So if you translate using this idea, this will give us that integral from x to infinity f of x dx, that is equal to c e to the power minus x over lambda. Okay, so that needs to be clear, because you see it's greater than equal to x, and the maximum x can go is like it's unbounded in the upper state, so it can go up to infinity. So if you think about x as, let's say, some kind of real line, it goes, so let's say this is 0 and let's say this is infinity. What is given is, what we need is that it always lies in this range. Okay, so it's greater than x and it goes till infinity. Okay, so the probability, if you integrate that, so this is the probability of finding, and that's given. Okay, so given this, we have to find what f of x is. So that is a mathematical problem that we have. Okay, so let's see. So we know that the total probability, so the total probability is given by integral 0 to infinity f of x dx equals, that we can write as 0 to x f of x dx plus integral x to infinity f of x dx by using the summation rule of integration. Like we just so what we are doing is we are considering the integral from 0 to infinity, and we split the limits from 0 to x first and then from x to infinity. Okay, so that's the thing, and this is the total probability and this is unity. Okay, so from here what we can write is the integral x to infinity f of x dx could be written as 1 minus the integral 0 to x f of x dx. Okay, so if you use this equation and substitute it here, what we get is 1 minus the integral 0 to x f of x dx equals c e minus x over lambda, or this could be rewritten in a slightly different way. So this could be written as the integral 0 to x f of x dx equals to 1 minus c e to the power minus x over lambda. See, the entire thing of changing the limits of integration from 0 to infinity to x is because now we will see from this we can compute what f of x, because we can take the derivative of this equation basically, and we can write a differential form of this equation and figure out what f of x is. Okay, so so this will become f of x dx equals, take the derivative with respect to x, so this will become minus c, derivative of exponential is exponential itself, minus x over lambda times the derivative of the, which is minus 1 over lambda dx. Okay, so if you see, what we get from here is f of x equals c over lambda e minus x by lambda. Okay, so we found out what is the probability density function and how it looks. Okay, so if we now know the probability density function, now it's quite trivial, as we did before, just imply the condition 0 to infinity f of x dx equal to 1 to figure out what c is. So we use this function, substitute here, do the integral and figure out what c is, put it back, so we then get to the total function f of x. So that gives us the probability distribution function. Okay, and similarly, if it is asked, find out the mean x bar or the expectation value of x, that's even straightforward, given that we now know f of x properly. So this is 0 to infinity x f x dx, and if it's asked, calculate the variance or the standard deviation, so we know the variance is the mean square, which is this, minus the square mean. So these all quantities can be computed. So this is computed from here, and x square, we know from before 0 to infinity, the second moment is x square f of x dx. Okay, so that's the crux. Okay, so let's see, there is given f of x. Now we know, question is find the fraction of molecules having x greater than equal to 2 lambda. Okay, so that what they're asking is p, what we want to find the probability of finding a particle at x greater than equal to 2 lambda. That is what we need to find out, and that is given by integral from 2 lambda, because x is greater than 2 lambda to infinity f of x. And this is based on the fact that we discussed before, that probability of x lying in between a and b is given by the integral from a to b f of x. Okay, so that's how we solve these kind of problems of probability densities involving probability density functions and other things. Okay, where we go, so it's quite simple, as you saw. Out of the standard procedure is same. Okay, now let's consider a little bit interesting problem, and let's see. This is a quite different kind of a problem, and here we will be basically diving straight into statistical thermodynamics. Okay, so the question is the entropy for Bose-Einstein and Fermi-Dirac statistics is given by S, that's a function of the total energy, the volume, and the number of particles. That is given by is equal to K, which is the Boltzmann constant, times beta E plus alpha n minus plus K. Let me write it like this: K sum over J Gj log 1 minus plus e to the power minus alpha e to the power minus beta epsilon j. Okay, where alpha and beta are the Lagrange multipliers. And n is sum over j of nj, and total energy E is sum over j nj epsilon j. Okay, so those are the things that is given. The question is find out the Lagrange multipliers. Find out the Lagrange multiplier. Okay, so in order to do that, we need to recall from our classical, so let's recall from classical thermodynamics. Recall classical thermodynamics, that we can write this expression ds of, we are using the same independent variables E, V, and N here. So ds of E, V, N is given of 1 over T dE plus P over T dV minus mu over T dN. Okay, so that is coming from classical thermodynamics. Okay, so given the form of entropy for Bose-Einstein and Fermi-Dirac statistics, and we know the definition or the differential of entropy from classical thermodynamics, what we need to do is we need to calculate this Lagrange multipliers. And you know that Lagrange multipliers are quite important, because those directly feed into the equilibrium particle distribution, okay, and which are used to calculate the final statistics, the Bose-Einstein or the Fermi-Dirac. Okay? So let's see how this to be done. So if you see from this expression, what you see is the partial of S with respect to E, so partial S partial E at constant V and N, that is given by 1 over T. So that's 1 over the temperature. Okay. So this is coming from classical thermodynamics, but so this right hand side is coming from classical thermodynamics. So what we'll do is this left hand side we will compute from statistical thermodynamics. Okay, and that because how can we calculate? Because we are given, so this is given. Okay, so the entropy for Bose-Einstein and Fermi-Dirac statistics is given by that expression. Okay, and how this expression is coming, that is derived in the main lectures. Okay, so refer to the main lectures where we talk about the partition functions and how entropy is related to the partition function and how this expression was derived for Bose-Einstein and Fermi-Dirac statistics. Okay, so given this entropy distribution S of E comma V comma N, what we can do is we can compute the partial derivative of the entropy with respect to the total energy at constant V and N. Okay, and if we do that, what it will become is partial S partial E at constant V constant N is equal to K times beta plus KE partial beta partial E comma N. One very important thing to keep in mind is the Lagrange multipliers alpha and beta, they themselves are functions of these variables E, V, N. Okay, so alpha comma beta are functions of E comma V comma N. So that's why when we are differentiating with respect to, let's say, E, we need to differentiate the Lagrange multipliers themselves with respect to E, keeping V and N constants. Okay, so if you see this expression, so the first term is quite simple because we are differentiating with respect to E. So the first term is just KB, but the second term, if you see, alpha can also be a function of K is the Boltzmann constant, so that's a constant, but this is then, so alpha can be a function of E, and N where we have this Kn. Okay, so K beta, so this becomes K beta, this becomes Ke. Okay, so actually let me rewrite the entropy equation once more here, just so that I can have some reference here before we do, because otherwise it's difficult to keep the bookkeeping. So let me rewrite the entropy is Se comma V comma N, which is K beta E plus alpha N minus plus Boltzmann constant sum over J Gj log 1 minus plus e to the power minus alpha e to the power minus beta epsilon j. Okay, that's given, and let's now do the partial derivative. Okay, so partial derivative of S with respect to E at constant V and N, realizing that alpha and beta are also functions of E, so they are also functions of E. Okay, so this become K beta, so that's the first term, plus K if you see, this is a product of two terms. We have B and E. So first what we did was we took this constant and we differentiated E with respect to E. That's why we have K beta, plus we have now K E, and now we need to differentiate B beta itself. So partial B with respect to E, V comma N, okay, plus k n partial alpha partial e at constant v and constant n. Okay, and you see one thing here, k and n as constant, that's why just we have a derivative of alpha with respect to e. Okay, and then we have minus plus the Boltzmann constant sum over j, and now we have to take the derivative of this inside term. Okay, so but now you see this is the derivative of a product, so it's the product of the gj times the log function. Okay? We do it one step at a time. So this will become, if we do, so if we take the derivative of the log, that will become 1 over, so let me write the denominator first, 1 minus plus e to the power minus alpha to the power minus beta epsilon j. So that's the derivative of the log, in which we kept gj constant, so gj goes in the numerator. Okay, and then we need to differentiate, so then we need to differentiate this entire term, which is e to the power minus alpha times e to the power minus beta ej, which is self. That's the same thing. It will become e to the power minus alpha times e to the power minus beta epsilon j. Okay, times, now we need to differentiate the powers of e, which is alpha, beta. Okay, so that will become, this is multiplied by, so that I will write down, partial alpha partial e at constant v comma n plus epsilon j, that is this thing, partial beta partial e at constant v comma n bracket close. See whether that term is clear or not. Okay, so if you see now, this term is the massive term, if you see this term, but if you realize this term we know actually from before. If you recall, for BE and FD statistics, the equilibrium particle distribution is given by Nj is Gj by e to the power alpha e to the power beta epsilon j minus plus 1. Okay, so that is the equilibrium particle distribution, and this could be rewritten as Gj e to the power minus alpha e to the power minus beta epsilon j all divided by 1 minus plus e to the power minus alpha e to the power minus beta epsilon j. If you see that this complicated term is nothing but that's Nj itself. Okay, so therefore partial s partial e with respect to v comma n is given by k times beta plus k times e partial beta partial e v comma n plus k n partial alpha partial e v comma n minus k. So now we are at this term. Okay, and minus k, and then we have, let's say, sum over j and j, where we just taking the one of the sign, which is the negative sign, which we are taking now. So minus k sum over j and j, and then we have partial alpha partial e v comma n plus epsilon j partial b partial e v comma n. Okay, if you see, and this is the final expression for partial s partial e, but realize that sum over j nj is n and sum over j nj epsilon j is e. So if you realize that, we'll see what this becomes is partial s partial e is v comma n, and so that becomes k times beta plus k e partial b partial e v comma n plus k n partial alpha partial e v comma n minus, and now if you see this is n basically, so this becomes minus k n partial alpha partial e v comma n. So that's the first term, sum over j, but if you have the second term is sum over nj epsilon j sum over j, that is e. So this becomes minus k e partial b partial e v comma n. And if you see, this term cancels this term, this and this gets cancelled, and similarly this term gets cancelled by this term. So what we are left is partial s partial e is v comma or v comma n at constant v and n is k times beta. And recall from classical thermodynamics we showed what that derivative was. That partial derivative was 1 over t. Okay, so that was 1 over t. From here we conclude that we found out one of the Lagrange multipliers, which is beta. So beta is 1 over Boltzmann constants times temperature. Okay, that's how we find the Lagrange multipliers. Okay, so next is, but remember we have two Lagrange multipliers, we also have to find out alpha. Okay, and that we will do in the next segment. Okay, so thank you.